Hello everyone, so I am Kshitij and today we will be continuing on from our last topic, laws of motion. We will be taking a deep dive into the concepts involving laws of motion and more of applications of laws of motion, and we'll be doing some questions as well. Alright, so we'll be starting with apparent weight. Sorry, sometimes I tend to misspell, sorry about that. Apparent weight, right? We have discussed this last time, but I want you to be able to understand it a bit better, right? Then we'll study about frames of reference a bit more. Okay, then we'll talk about the validity of the three laws, because you really need to understand what's going on. All right, then we'll see what Lami's theorem is. Okay, Lami's theorem is kind of like the law of sines but in vector form. Okay, then we'll see impulse and change in momentum. Momentum is represented by P, so I'll just put in small p. Okay, now when we talk about physics, we have different P's. So one is momentum, one is pressure, one is power, and we'll be using two of these today. Okay, so keep that in mind. Okay, so once we are done with impulse and change in momentum, we'll be talking about in impulse and change in momentum, we'll also be seeing kind of graphs of force and momentum. Okay, very basic, not very advanced, because the advanced ones are basically developed on these basic graphs, right? And they are more about solving questions, so they are question specific. So we'll be doing the basic ones to understand how to utilize these graphs. All right, okay, then we'll be seeing motion of connected bodies, motion of connected bodies. Then we'll see what is the procedure to make a free body diagram. Right, free body diagram is what helps us isolate different components in any question, right, and apply forces basically what are there on the objects, and then calculate our questions accordingly, right? Then we'll see tension of string. Most of the topics today are question oriented, right, rather than pure theory, right? Because today we are going to understand the concept we discussed in the previous class and dive deeper into the applications, as I said before, right? Okay, so next we are going to see constrained motion. Then we are going to see simple Atwood machine. Right, then we are going to see spring force. Keep on misspelling P and R, I don't know, sorry about that. Spring force, and in that we'll also see what is the extension of spring from equilibrium. Right, then we'll see string versus spring, very small topic. Okay, after that, string versus spring, we will see string cut. String cut will be more of question based, so purely question based. Then we will see combinations of spring. Alright, then we'll see recoil of gun, and the last one will be rocket propulsion. Are you excited for this? Everyone is usually more excited about space than actual physics, so I reckon that you'll be enjoying the last topic more than the others, right? Okay, so let me put this duster down. So we'll be starting with apparent weight. So let's see what apparent weight is. Again, oh my god, am I illiterate or what? Apparent weight, right? Okay, so if you remember, last time we were talking about a lift, right? So when we are in a lift, our frame of reference changes, right? So we are in the lift, someone is watching us. So the person who is watching us, he is in an inertial frame of reference, and when we are in the lift and we are observing ourselves, so we are in an accelerated or non-inertial frame of reference. All right, so let's think about that for a moment. Okay, let us imagine that we are this block. See, I changed from the person to the block because it's easier to draw the block, okay, taking shortcuts, right? So imagine you are this block, and this block, it has some mass. Let us say it has mass m. We are not taking into account the weight of the lift because we are just trying to focus on the person themselves. So we are being narcissistic, enjoying my narcissistic tendencies. Right? Okay, so why am I discussing this? Because this is kind of an anomaly. Anomaly is what? Anomaly is something different from a regular thing, right? So when we started talking about laws of nature, we said that a law is a regularity of nature, right? It's based, it describes a regularity of nature. It's not a regular, it describes a regularity of nature, right? So what happens is, according to the first and second laws, right? If you observe, we have this weight, it's called m times g. M times g is the weight of the person when they are in the state of rest, well, relatively, let's say from an inertial frame of reference, they are in a state of rest. Okay, so but in this condition, let us say the lift is moving up and the acceleration is upwards. All right, now what is happening is, this person inside, he's looking at things outside. Okay, so things outside, now to him, he is going up, but to him things are going down, right? So to him things are going down. It is very much comparable to the concept of relative velocity. So imagine, you can break it down. So you are sitting in this train. Okay, let's imagine that this dot is a train, and this train is moving forward at a speed of 5 meters per second, right? And then there is another train moving along the same track, and it's moving along this track at 10 meters per second. So if you remember the concept of relative velocity, though I have not taught it yet, but if you are watching this video, I am assuming you know the concept of relative velocity. So you are moving in this direction, and the train, or the opposing train, is moving in this direction, opposite to you, right? So what will happen is, you are looking at this train from your frame of reference. No, we are not talking about inertial or non-inertial frame, just your frame of reference. Okay, we are assuming that these are constant velocities, right? So when you look at it yourself, so you are at rest according to you. Okay, according to you, you are at rest. But the amazing thing is, this train, it is moving at a different speed according to you. And how much is this speed? Because you are moving in this direction and the train is moving in this direction, right? You think of yourself at rest, and that other opposing train, it's moving at a combined velocity. Had you been moving in the same direction, then the magnitude of this train according to you would have been the difference. Okay, so imagine if this sign was in this direction, okay, the train was moving in the same direction as you, right? Then this would just have been 5 meters per second. Okay, but as it's moving in the opposite direction, the direction would have been this. So this is the concept of relative velocity, easily understood. Now apply that to this lift. Okay, so you are at rest, forget about this weight right now, okay, and you are moving up, but according to you the world is moving down. So whatever your weight was, if you think about it, it was 0, right? That was 0 because of acceleration due to gravity. So when you were at 0, you had an acceleration due to gravity g, but now you are moving at an acceleration upwards. So that acceleration automatically gets added because you are moving in opposite directions, right? This acceleration gets added. And what's your mass? Your mass is m. So if you think about it, apparent weight is more of the concept of relative acceleration, nothing more, right? So keep that in mind whenever you're solving questions. I hope this is clear to you and you're starting to get the feel of laws of motion. You're able to understand what physics is. Okay, this is why when the lift is going up, you feel heavier, right? Now as you're feeling heavier, let's think about it again for a moment. Here is this lift. Sorry, I forgot to bring in the different laws, but okay, let's just we'll be discussing it later. So let's just talk about the next topic. We'll bring back the lifts when we will be discussing the validity of the 3 laws. Okay, so I hope you understood that. Now let's talk about the frames of reference a bit more. Okay, frames of reference. Now I know this is again, let me just check if it's recording. Sorry. Okay, it's recording. Okay, back to the topic at hand, frames of reference. So frames of reference. Now imagine we have this frame S dash. We don't know that if it's in an accelerated free state or a non-accelerated state. Okay, and we have an inertial frame of reference S. Okay, so someone is here and there is this particle P. It's moving with some acceleration, let's say A. Okay, so now I'm going to use vector form for you to be able to understand a few things, right? So this acceleration is a vector. Okay, now let's see from the frame of reference S. Okay, let's call this 0 0. Okay, S dash is somewhere over here, somewhere over here. Okay, S dash is somewhere over here. Okay, and P is somewhere over here, right? Okay, now let's join these vectors. So according to the acceleration of S dash, according to S, we can call that A S dash S. The acceleration of S dash with respect to S, that can be written as S dash S. Okay, the acceleration of P according to S, according to P, according to S, can be written as vector of A PS. Similarly, we have A S A P S dash. All right, so we have this small triangle. Okay, now direction of S dash S will be towards S dash. Okay, because we are measuring this frame of reference, magnitude of this frame of reference. Similarly, when we write PS acceleration, the arrow will be in this direction. and similarly ps dash, this becomes this. Okay, so if you think about it, aps dash, you can see, sorry, aps, it is the resultant of a s dash s, okay, and ps dash, right? So we have this formula, kind of, not, it's not an exact formula, it's just vectors, all right, just vectors. Now you're looking at vectors. Now if we'll take two cases, when s dash is moving uniformly according to s, then this value becomes 0, right? Then this just says a vector of aps is equal to vector of aps dash. What does that mean? This simply means that s dash is also an inertial frame of reference. Okay, so if you think about it, if s is earth and s dash is you at rest, right, or moving at a constant velocity, so to you the acceleration of particle p will be the same as it is to earth. So that's how this dynamic works, you know, so that you are not able to tell what is the difference. Okay, now let's say if this s dash is an accelerated frame, okay, accelerated frame, so this will have some value, s dash. So in that case you will have to consider this value, and this value will be different. So aps dash will be equal to aps minus as dash s. Okay, right? So this kind of proves that in accelerated frame of reference we will have different values. Okay, right? It's a bit more detail into that, but I'm not going to move into that because so many people are watching this, not so many, like a variety of people will be watching this. You can basically use this to prove this, but it's not needed. You can see here, this is a non-zero value, so difference is here right now, and this acceleration is non-zero, right? So as this is non-zero, this is an accelerated frame of reference. Okay, simple. As the difference in them is non-zero, therefore the value for ps will change, right? Okay, we discussed apparent weight, we discussed frames of reference. Let's talk about the validity of the three laws. Okay, so as I mentioned before, the first law is not valid when you are in an accelerated frame of reference. Why is that? Because the first law, if you put in vector form, it's nothing but f dash, if f net is equal to 0, then acceleration is 0, right? But if acceleration is non-zero, then net force is also not equal to 0. Simple, right? Okay, but what does that mean? It means that if acceleration is non-zero, the net force has to be 0, right? And this is what the second law helps us with. Okay, so f net is proportional to mass times the acceleration vector. considering if the object is not losing mass, right? It's not a variable mass system, it's a uniform mass system. Okay, so this is what it is. So if you look at this mass is constant, right? This mass is constant, so therefore F net is directly proportional to the acceleration, to the net acceleration. So if acceleration is 0, F net must be 0, right? But here's the problem. If you remember the weight of the lift, right? Apparent weight right here. Okay, now this is accelerating upwards. The normal weight is mg. Now think about it for a second. This lift is accelerating, right? But to the person inside the lift, he is in an accelerated frame of reference. To him the lift is not accelerating, okay, but he is experiencing an increase in the weight. Let's call it mg plus ma. So even though there is no acceleration, he is still experiencing a force. So this law also becomes invalid, right? So the first two laws, they lose meaning when you talk about an accelerated frame of reference. I wanted to give a clearer description to this. I had mentioned this last time in some form or the other, but this makes it much clearer. Okay, so the third law, F dash AB is equal to minus of FBA dash. Okay, so imagine you are this block again, you are putting force mg on this earth, right? And the earth is putting a normal reaction back at you, whose magnitude is mg, right? But it's opposite in direction, that's why the minus is there. Okay, clear? But this is also not strictly correct. Why? There are a few reasons. Reason number one, gravitation is technically not a force. Not a force. It is a curvature of space-time. And as it was proven, the forces, they are not instantaneous. Okay, so what that means, you are applying this weight mg onto it, the earth is applying a normal reaction back, but what is that normal reaction? That normal reaction is nothing but electromagnetic force of this edge of the earth. The electromagnetic force of the edge of the earth, it is providing a normal reaction back to your gravitational force, right, that you are putting on the earth. Even though it is equal in magnitude, this does not happen instantaneously. Okay, so this is not strictly correct because of that. One reason is this. Another thing, if you think about light, okay, it's an electromagnetic wave. So electromagnetic waves, they can store momentum, they can store energy. So what happens is, when light is traveling, okay, and it collides with any surface and it experiences a reaction to it, right, what is happening is this force is being applied to the photons of light, but these photons, these waves, they store that momentum, they store that force, they store that energy, right? And after a small period of time, that change in momentum gets reflected. For that brief moment in time, there is, it's not instantaneous, the momentum kind of disappears. Okay, so not disappears exactly. So what happens basically, it decreases gradually, and then it comes back to where it was. Okay, so this is what happens. Therefore this is not instantaneous. So assume that 10 joules of energy was transferred from the photon to the wall, right? So this, what is happening is, this photon is not transferring that energy back instantaneously. Sorry, not energy, not transferring that force immediately back. What is happening is, it's receiving that force slowly, but according to this law, it should be transferred immediately. So that's why the three laws, they have validity, but in some way. But when we'll be studying in this classical scope, right, we will be assuming the correctness of these laws, but in some situations we will have to observe the invalidity as well. So in your coursework, we will be using situations where the first two laws will be incorrect, like the apparent weightlessness of the lift. Okay, so three laws. Let us talk about Lami's theorem. Okay, so let us assume there is this particle O. A force is on it, let's say vector F1, another force F2, and another F3. Okay, so the angle opposite F1 is alpha, the angle opposite F2 is beta, and the angle opposite F3 it's gamma. Okay, so what does Lami's theorem state? Assume that this particle O is in equilibrium despite the forces acting on it, right? So what will happen is, the ratio of F1 to sine of alpha will be equal to F2 to sine of beta will be equal to F3 of sine of gamma. Okay, that's what Lami's theorem is, nothing more. You can write it down. Okay, okay, pause and write it down. So coming to an important topic, impulse and change in momentum. Change in momentum. Okay, what is impulse? So imagine, you don't have to imagine actually. If you remember, I have put a post on my Instagram. So what that discusses is what happens when two bodies collide, and even though the bodies are moving uniformly, still there is a change in velocity, there is an acceleration. Why? Because of some force. Now that force, it's the impulse, right? And impulse is nothing but, imagine if a large force is acting on some object, okay, then over a small period of time that object experiences a change in momentum. So the average of that force will be multiplied by the change in time, you know, the change of that momentum, it occurs in a certain period of time. So we'll call that delta t. So multiplied by that becomes the change in momentum. Okay, and this is called impulse, right? Now we have two basic graphs. One is this, force and time, another is momentum and time. Okay, so if we have to see what the impulse is, so imagine there is this graph, variable graph. Okay, so the impulse will be the area under this curve. Okay, let's call this graph A. Impulse will be represented by delta p, so it's equal to area under the curve, right? When we talk about momentum or change in momentum, you can measure impulse in this graph directly, right? So there is this curve, right? So at this point there is this slope. So at this point, okay, there is this angle theta. So if you know that this will help us calculate the slope in this angle, in this graph, sorry. So tan theta will be the slope. If you know y is equal to mx plus c, right? M is the slope. So tan theta is the slope. So at that particular instant, let's say z, at instant z, right? Tan theta will be the force at that instant. Okay, why? Tan theta is what? Tan theta is what? Tan theta is perpendicular by base. So theta is this. What is the perpendicular? Perpendicular is the change in momentum, and base is what? Change in time. So f dash is equal to delta p by delta t. Isn't that correct? Okay, right. So there are different ways of doing that. You just need to get this tan theta value, and this will help you. And in this case, if you want to calculate change in momentum or impulse, you can just take the area under the curve, right? Okay, one very important thing which comes in exams, direct question comes. Okay, direct question. So let's do that concept. It's like wall collision, right? Wall collision. So you have to remember, when we work in physics, we use vectors, right? So imagine this is a wall, and the wall is getting struck by a ball. Okay, it has some velocity v, right? The angle with the wall is theta, and the angle to the normal, point to be noted, this is the normal to the wall where the ball is striking. Okay, that is alpha. Okay, now we have two situations. One where this is an elastic collision. If this is an elastic collision, what will happen? The kinetic energy will not change. There will be no loss of energy. So no loss of energy. Loss of energy is equal to 0. What that means is the reflected velocity will be the same in magnitude as the initial velocity. Okay. Okay. So this will also be theta, and this will also be alpha. So let us see what the velocity vector was before. Okay, instead of velocity vector, let's just see what the momentum was before. So let me write down initial momentum as vector of pi. Okay, now note, the mass of the ball is not changing, so only one component. So mass is constant. So let us see, take m outside. Okay, now this is in two coordinates, right? So we have two unit vectors, I and j. Okay, I cap and j cap. So I cap will represent the x component, and j cap will represent the y component. Okay, so the y component initially, okay, what is that? That becomes v cos theta. Okay, v cos theta, but downwards. So as it's downwards, think about sign conventions. When we talk about sign conventions, if it's downwards, it becomes negative. So the y component is negative. Okay, and the x-axis component. Okay, now x-axis component is right here. Okay, right here, right? So if this was v cos theta, this becomes v sin theta, and it's moving towards the right. So as it's moving towards the right, it's positive. So we get v sin theta I cap plus, sorry, not plus, minus v cos theta j cap. All right. So this is initial. Similarly, we will get pj cap, p vector of final. Okay, so m is constant, v is constant, but what is happening now? Now this v is here, right, and the y component, right, it's still v cos theta and it's still downwards. So this remains as it is, but this is moving here, right? So the component comes here, right? It's moving in the opposite direction. So this also becomes negative, and this becomes minus v sin theta I cap minus v cos theta j cap. Okay, let me remove this from here and I'll put it right at here. Okay, so this becomes the final momentum. So delta p, now as you can see, the y component, it's not changing, which is quite obvious, because the ball is moving kind of downwards. It's not going up, it's moving down. So obviously the y component is not changing, right? Because gravity is not working in that. Let's assume that, okay? But we'll see that. Right now, in this case, gravity is not affecting it. So this remains the same. Now, what is the change? This is the change. The x component is changing, right? Therefore, what we get? We get delta p as 2 mv sin theta. Okay. Also, sometimes what they'll do is, instead of showing you this angle, they'll show you this angle, right? So you can also write delta p as 2 mv cos alpha. Okay, simple enough. Sorry, I went a bit out of camera. Simple enough. Now let us assume the loss of energy is not zero. What will change in that? Okay, what will change in that? The velocity changes and v2 becomes less than v1. So p vector I, we had the x component was positive, so mv1 sin theta, right, mv1 sin theta I cap, and minus mv1 cos theta j cap. Okay, now I just, instead of taking it common, I put it outside, and pf is final, right? So minus mv2 sin theta I cap minus mv2 cos theta j cap. Okay, now it's very similar, you just added the 1 and the 2, but it gives a very big change. Okay, so this might not come, the first one comes a lot. If this comes, you can use this formula, there is no shortcut to it. Okay, the first one is kind of a case of this, if you think about it, because v1 is equal to v2. So if you take v1 is equal to v2, you will get the same result. All right, same result. So let's do a question. Let's do a few questions. Okay, so question 1. Now a bullet enters a block of wood with speed u. The question will be somewhere here on the screen. Okay, so bullet enters a block of wood with speed u. Block of wood. Okay, with speed u, and after traveling 2 centimeters into the wood, so this is 2 centimeters, its speed becomes half, u by 2. So what is the total distance that the bullet travels before coming to a stop? So at this point the velocity is 0. Okay, So v square minus u square is equal to 2as, right? So v is u by 2, so u by 2 becomes u square by 4, right? Minus u square is equal to, acceleration is negative because it's reducing the velocity, so minus 2a, and s is 2 centimeters, so acceleration will come in centimeter by something, right? So we want to calculate the distance anyway, so that's all right. So we get 3u square by 4 is equal to 4a, okay, and a is 3u square by 16, right? So we get a. Now we have to calculate x. X is what? V is 0, u is u, so 0 minus u square is equal to minus 2 into 3u square by 16 into x, right? So u square is equal to 3u square by 8 into x, okay, u square gets cancelled, x comes to 8 by 3 is equal to 2.67. Right, this is the answer. That was the first question. Let's move on to the next one. Question number 2. Let me check. Sorry. Yeah, it's recording. Let's move a little faster. So question number 2. Okay. So ball of mass m is dropped from a height h. This is h, this is m. Ball of mass m is dropped from height h, strikes the ground and rebounds up to same height. Okay, so it comes back to the same height. Okay, so magnitude of impulse. Okay, so as we know, under free fall, the velocity of the object just before striking the ground is what? Root of 2gh. Okay, and as is going up to the same height, so it will have the same velocity after rebounding from the ground, therefore that will be v is equal to root 2gh. Okay, vf and vi, but they are in opposite directions, so difference becomes 2mv. V is what? 2gh, so 2 root 2 or 2m root 2gh. This is the answer, right? Very simple. Okay. Okay, next question. Now I have kind of customized this question. Question number 1, the bullet one was from NEET 2023. I forgot to mention, sorry. Second one was not from NEET, I just made that question. Now this question, question number 3, okay. These are two parts to this question, so it's combined. So it's the same thing, ball of mass m, okay. It collides the wall without losing velocity, so v and v, right? Okay, and the angle with the normal is 60 degree, right? So magnitude of impulse, nothing but delta v. Delta v will be what? 2mv cos alpha. Note this is alpha, not theta. So cos 60 is how much? Cos 60 is how much? 1 by 2. So delta p is equal to 2mv into 1 by 2 becomes mv. So delta p is equal to mv. That's the first part. Okay. So this was in the NEET 2016, I think. 2016, yeah, in the second set. Okay. Now the second part. What is the direction? What is the direction? So very simply, The y component has not changed, so it's still moving downwards. Okay, now it is moving to the left in the x coordinate, so it's moving to the left, it's moving in the direction. How will you point it out technically? So mv, so x coordinates change, so x mv, so sorry, the direction is just to the left, the angle is 30 degrees. Okay, very simple, that's all. I don't want to make it too complicated for you right now. Okay, so we are done with impulse. Let's do motion of connected bodies. What's the time? Sorry. Okay, motion of connected bodies. This is also more of a practical application kind of concept. Practical in the sense that it's directly applicable to questions. Okay, so we are going to take this frictionless surface because right now we have not studied friction. Okay, we have not studied friction. So we have m1, m2, m3. A force is applying, okay, of some magnitude. Okay, and these blocks are moving in the same direction as the force with an acceleration a. Now m1 is applying some normal reaction n1 and m2 is applying this back. Okay, similarly m2 is applying n2 and m3 is applying n2 back. Okay, right? Okay, so we cannot think about this right now. We'll just think about the edges kind of. Okay, so when we talk about n1, if you think about it, there's this m1. Okay, it's experiencing this force F, acceleration is in this direction, right? And it's, what is it experiencing? What, not it's applying, what it's experiencing? It's experiencing this force n1. Net force is what? ma. So m1a is equal to what? m1a is equal to, now F is in the direction of that, so F minus n1. Okay, so n1 is equal to, n comes here, F m1a, F minus m1a. Okay, first one. How do we get? Now let's talk about m3. Now m3 is moving in this direction, moving in this direction with an acceleration of a, and what? It's experiencing a normal reaction in the same direction. So can we write n2 is equal to m3a? Right? So with the help of these equations, we can calculate the motion of connected bodies. Okay, let's do one question. Right, let's do one question. Now this question is from NEET 2024. Okay, very simple question. There are only two bodies. Okay, this is a force of 10 Newton, right? MA is 2 kgs, MB is 3 kgs, and it's moving in this direction with an acceleration a. Alright, so let's get, as we have the values, we can find out what the acceleration is first. So F net is what? 10 upon MA plus MB. Alright, because this is a force that's getting applied, and think of this as a single block, right, of the combined mass of these. So 10 by 5, this was 10 newtons, this was in kg, so we get an acceleration of 2 meters per second. Now let's make the diagram. MA and MB. Okay, now MA is here, right, MA is here. MA is applying a normal reaction on MB, and MB is applying that normal reaction back. Okay, so MA is experiencing an acceleration in this direction. Okay, acceleration in this direction, and it's experiencing a normal reaction back. N. Okay, so normal reaction back. So, and this is the force it's experiencing, that's 10 newtons, right? Force of 10 newtons. Okay, so it is moving in, the force is applied in this direction only. So MA is equal to 10 minus N. Very simple, similar as before. Okay, this is one equation. MAA. Now let's look at B. It's moving in this direction with an acceleration A, and it's experiencing a normal reaction in the same direction, so we can write N is equal to MBA. Okay, MB is how much? 3 kgs, and A is how much? 2. So it's experiencing a force of 6 joules. Okay, so 6 joules. Oh sorry, Newton, sorry, my bad. 6 Newton. 6 Newton, wait, so 6 Newton. Now forget about that for a moment, let's check here so that it should be the same. So M is 2, acceleration is 2, 10 minus N. Okay, so N is equal to 10 minus 4 is equal to 6. We get the same thing. 6 newtons is the answer. So this was about motion of connected bodies. The questions we are doing are important, but they are basic, so that you can enjoy and be able to solve these easily. Okay. Now let's talk about free body diagram. Okay. Now when I was doing that question, you assumed that to made a dot and added forces. That's kind of how we make the free body diagram. So imagine there's this boy. He is holding a weight up on the floor. Let's forget about friction. This load is of some mass, okay, mg. The boy's mass is m, so his force is mg. He's experiencing. Okay, so there are a few steps. First we have to choose the system. Step 1, choose the system. This is how we will be able to calculate these things. Okay, now when we actually solve questions, we don't follow these questions exactly, these steps exactly, but we kind of condense these steps. Okay, I will show you later. Now once you have chosen the system, choose the think about the forces which are being applied to those systems. Okay, forces. Then you make a free body diagram. Okay, then you write the equations used by, choose a coordinate system, and write the equations. Okay. Okay, so let us think about the systems. The first system is the load. It's experiencing a force by this boy, so it's moving up having an acceleration a, right? Its mass is n, so ma, right? ma is experiencing this and its weight is downwards, so mg. Okay, these are the forces on the load system. So let's write this down. System and load and forces. Okay, very simple, right? So you talk about the load, you have two forces, the weight and force by a buoy. Now next we talk about the buoy. The buoy, now he is experiencing weight of load. Okay, right? And he is experiencing normal reaction from floor, normal from floor, and he is applying his weight to the floor. Okay, simple. So three forces. So let's make the diagram for the load. So load is here, load is here. Okay, so ma upwards and mg downwards, right? Now we have to choose a coordinate system. Generally what we do is we take the direction in which the body is accelerating, okay, and we take that as the x-axis, but I don't recommend following that exactly. What I recommend is just always what you do is follow the 2D system. So it's moving up, so think about it as y-axis, and to the right you take x-axis. Okay, but just to follow the system, to follow tradition, let's think about it as x-axis. So this becomes, if you notice here, there is only one axis. Okay, one axis, so it's a 1D system. So up and down, net movement is up. Okay, so let's take that as positive. So oh my bad, sorry, it's experiencing a force upwards and it's experiencing an acceleration upwards. Okay, so ma is equal to f minus mg. Now it's correct. I was wondering why I was feeling wrong. Yeah, so ma, it's the net acceleration experienced by the load, right? Force is the force applied by the buoy to the load, right? And mg is the weight of the, therefore the acceleration will be in the up direction, that is positive, this is negative. All right, okay. Now let's talk about the buoy. Let's talk about the buoy. Now what is happening? The buoy does not have any acceleration. Okay, the buoy is experiencing this weight downwards, okay, mg, and is experiencing a normal reaction according to his weight, that is equivalent to mg, right? Also he is applying some force F upwards, okay, which is acting opposite to mg. Okay, so these and these cancel out, right? And he is applying his own weight to the floor, that is mg, so these and these cancel out, so net acceleration comes out to be 0. Okay, let me put it again so that you don't get confused, because there are a lot of forces involved here. Okay, this is the buoy, the load on him is mg. Okay, but if you note, he is cancelling that note out with the force, right? The force is cancelling that out and providing an acceleration upwards, and he is exerting a normal reaction in the weight downwards mg and a normal reaction upwards, that is same. So this is getting cancelled out, and this is providing an acceleration to the load A. Okay, so the boy is not moving himself, therefore these normal reaction and the weight get cancelled out, and at the end what we get, acceleration is upwards of the body, not the boy. So acceleration upwards, we again get ma is equal to F minus mg, same thing. Okay, so that's how you make a free body diagram. Okay, free body diagram. Okay, do we have questions on this? No, we don't have questions on this. Let's talk about tension of string. You don't need to worry about it exactly, because making a free body diagram is complicated. You need to ponder a lot and think about the forces, because if you don't think about the forces, the acceleration, it will all get messed up. You need to take everything into account, the movement as well, otherwise it will get ruined, right? So tension of string. Imagine there's this wall, ceiling upwards, there's this string, and there's a weight on this string. There's a point A. Okay, now we have a few assumptions. One, that this string, it's inextensible. What that means is this load is being put downward, right? So it should cause some change in length, but this is not happening. That's why it's called inextensible. Okay, sometimes we will assume that this is massless, not right now, but it can be assumed. Okay, so now when we talk about tension, what is tension exactly? Tension is the electromagnetic force, right, putting at the edges to prevent the string from extending. Okay, that's why it's inextensible, due to the electromagnetic force. Now the weight is applying here, right? Therefore it's trying to pull it downwards. So to balance that out, an equal electromagnetic tension is applied upwards here, but the pull is not only here, the ceiling also tries to pull it up. Okay, right, because of this weight. Therefore the string applies a tension downwards, right, to pull the ceiling to itself. That is the same, because the pull is mg only. Okay, now as we are assuming that this is not massless, right, therefore this let us say that this block is of mass m. Okay, this block is of mass m, and at the end of the string, the whole string, this is experiencing a weight mg, right? But at this point A, okay, at this point A, how do we say what is the tension at this point? Okay, so let's think that the tension at this point is T dash. Okay, T dash. Okay, the system has changed, therefore the forces will change. The mass of this string becomes, let's take it small m. Now the total mass of this becomes m plus m. Okay, so at this point A, it is experiencing a weight of m plus mg, m plus m into g. Okay, this is the weight it is experiencing. Therefore the tension T dash applied at this point, it's equal to m plus m g. Simple enough. So if we talk about this point A, the tension is the mass of the string below that point plus the mass of the object into the acceleration due to gravity. But if we talk about the full length of the string, okay, at the end, at the edge, the tension becomes mass of the block into acceleration due to gravity. Okay, this is what the tension of the string is, right? Let's do a simple question, right? Question number 5. Now imagine if a boy is standing right here and he is holding this string with this mass attached to it. Let's call it M. Okay, let's call it M. And there's this point A, right? Now this system is accelerating downwards at A, right? So what are the different tensions at this point A and here? Now we can do it two ways, or we can do the shortcut, right? If you remember, when we talked about lift, when it was moving upwards, like the acceleration was upwards, the weight added, right, by the acceleration, and if you move downwards, similarly the weight will get reduced. So this system is moving downwards, right? And now two cases. Let's take T dash as the point A. Okay, so T dash will be, what will be T dash? It will be equal to the weight experienced at this point. So what is the weight? Weight is M plus M. Let's call this weight M and this weight M. The mass of the string below that point A is M, right? So M plus N, that's the mass. And as it's moving downwards, the acceleration is G minus A, because G is due to gravity and it's moving downwards. So we get a pseudo force upwards that subtracts from M plus M into G. We get this. And similarly, if we talk about this edge, right, the edge of the string at the end, the only mass we have is M, therefore we get M into G minus A. Okay. Now this was the quicker method, if you remember it, right? Think about the lift, that's how you will get it. Okay. Now let's make the free body diagram. Okay, we will take both situations and we'll calculate the tension. So tension is upwards, T dash, right? Weight is what? M plus M into G. Okay, acceleration is downwards. So here comes the learning point. Okay, or here also you can think about two ways. So acceleration is downwards, so net force is net force is M plus M into A, right? This is equal to M plus M into G minus T at T dash, right? Because T dash is upwards, so T dash comes out to be what? Same thing, T dash is equal to M plus M into G minus A. Same thing if you will calculate it. Okay, another way what you can do is, acceleration is downwards, so you apply the pseudo force upwards, M plus M A, right? So what equation we will get? We will get M plus M into G is equal to T dash plus M plus M into A, right? Is what it is similar to what? Same thing as upwards. If you look here, right? So the T dash is just here. Okay, look at it, right? So we will get same thing. Now make another diagram. Let's calculate T. So T is up, right? The mass is down, mg. Acceleration is what? Down. So what do we get? We get ma is equal to mg minus t. So t is equal to m into g minus a, right? So what's the answer? M plus m g minus a comma okay, m into g minus a, right? These are the tensions at point A and at the edge, right? Simple. Okay, this was tension of string. Tension of string. Now let's talk about constrained motion. Constrained motion. Okay. What is constrained motion? When we talk about constrained motion, we have a few assumptions in most cases about the string, okay? Because mostly constrained motion involves a string or a rope, okay? First is the string is inextensible. Okay, if it's not written, three assumptions: inextensible string, massless string, and frictionless pulley, okay? So inextensible string. When we talk about constrained motion, we have two different kinds of things when we talk about different competitive exams. Let's talk about the JEE one first, NEET one first, okay? So we have this pulley, there are these two loads, okay, right? This is experiencing a tension T1, this is experiencing a tension T2, right? An acceleration A1 and an acceleration A2, right? Now, thinking about this, the formula for power is work done upon time, which is also equal to force dot displacement upon time, which equals to force dot velocity. Okay, fine. Why are these vectors and this is not? Because this is a dot product. Dot product is scalar, right? So in this case, this is being observed, okay? In both the NEET and JEE cases, we'll observe this, but there are different consequences as a result of this equation, okay? Now, we get this, right? But as the string is inextensible, the work done by it is zero. Therefore, F dot V becomes zero. Okay. Now, if we differentiate, before differentiating, we take the force here is tension. Okay, and we are taking zero because it's a sum of these two, right? The work done in total is zero. It's not that T1 dot V1 will be zero. No, the sum of these two will be zero because this moves up and this moves down. The net displacement becomes zero, right? Therefore, the net of this work done becomes zero at that point. Therefore, T1 dot V1 plus T2 dot V2 turns out to be zero. Okay. Now, if we differentiate this with respect to time, we get T1 dot A1 plus T2 dot A2 equal to 0. So when solving questions in NEET and constrained motion, this is what you'll need to remember. Why I will be explaining the JEE thing? Because it's related to this and it's not very complicated. We will need to use relative velocity. Okay. Now think about the same pulley, right? Same pulley. Let's call it P, right? This weight here, let's call it A, and this weight here, let's call it B. Okay. They are both, let's assume the velocity of A is upwards, velocity of B is upwards, and velocity of the pulley is also upwards. Okay, these are the assumptions we are taking. Now the net displacement was 0 of this string, so dx, let us assume the change here is dx1, x1, this is x2, right? So the net change over time in the overall displacement of this is 0. So dx1 plus dx2 is equal to 0. So VA plus VB is equal to 0, right? No. Why? Because we are right now, this becomes relative, okay? Because the pulley is also moving. So this does not equal to VA. V1 will be the speed of A with respect of P. Okay, how much that will be? That will be VA minus VP. Okay, because both are moving up, right? These are the assumptions. Now if the assumptions change, we can just change the signs because they are vectors, right? So VA P, okay. VBP similarly becomes out to be VB minus VP, right? Okay, so VAP plus VBP is equal to 0. Now let's put these back together. So we get VA minus VP plus VB minus VP is equal to 0, right? Because VAP is equal to dx1 and this is equal to dx2 at the end. Therefore we get VA plus VB by 2 is equal to VP. Okay, let me just write it here. So this becomes VA plus VB is equal to 2 VP. Okay, these two VPs add and come here. Therefore we get, okay, the final equation. So this is for JEE. But if these concepts they switch for your exam, now you can study for both of them. Okay, very simply you can use this. Right, let's do a question. Let's do one or two questions. Okay, question number 6. This is a bit bigger, right? Okay, now to solve this question, we will need to use some trigonometry. Okay, 37 degrees is here. Now I have a live stream which I have recorded in which I have explained basic trigonometry. You can use that to understand what I will use. Okay, so the velocity of A is 8 meter per second, but as this is constrained motion, you have to understand when the string is same, right? String is same, it's taut, it's not low, it's not loose, it's not lagging. So the velocity of this block will be the same as the string, and the velocity of the string will be the same on all points, right? Therefore this is 8, so velocity at all points across the strings is also 8, right? Now 37 degrees, right? So this is 8, this is VB, and this is 37 degrees. So how will we find out VB? The component of VB at this string is what? VB cos 37. Okay, it is on this, so therefore this is equal to 8. Now cos 37 is nothing but 4 by 5, so VB into 4 by 5 is equal to 8, so VB is equal to 8 by 4 into 5, this equals to 10 meter per second. Solved. Easy. Okay, let's move quickly, we don't have a lot of time. Let's do question 7. Okay, this one is, don't worry by looking at this figure. Okay, we have two blocks A and B, right? This block is moving with velocity v naught. Okay, we have a pulley here and we have a pulley here. Let's make it a bit longer. We have a pulley here. Okay, right, I have a pulley here and this, right? Now you have to note this is just one string. Okay, so constrained motion is being applied. Now as same string is there, tension is here T, this is T, also here T, so T is there, right? Therefore there is T here, 2T is here. Okay, so this block is experiencing 2T here, and also since along the same string, so there is another T here, so B is experiencing 3T tension. Okay, so TB is equal to 3T, right? And this, we have 1T here, 1T here, so TA is equal to 2T. Now velocity of A we have to find out, right? Velocity of A we have to find out. Okay, so if you remember constraint of string, so T1 dot V1 plus T2 dot V2 is equal to 0. Now you have to remember the surface is frictionless, all right? Now therefore TA dot VA plus TB dot VB, it equals to 0, right? So 2T dot VA plus 3T dot VB equals to 0. Now these forces at 90 degree, therefore this becomes 2T VA plus 3T VB. VB is V naught, so we get 2T VA plus 3T V naught equals to 0. Now T and T cancel out, so VA is equal to minus 3V naught by 2. V naught is towards right? Yes, let me do it again. So 3V naught comes here and 2. TT gets cancelled. Yes, So VA is minus 3 V naught by 2. Therefore, as it's negative, V naught was positive, so it moved towards, experiences a velocity towards the left. Does it do? Yes. So it will experience a velocity in the opposite direction. Okay. T 2t dot VA 2t dot VA plus 3t dot VB. VB is to the right. To the right is 0. Yes. Okay. Okay, so we are done with constrained motion. Let's talk about simple atwood machine. Now this concept can be used directly to solve questions as well. I'll do the derivation real quick and we'll do a question and then we'll move on to the next topic. Simple atwood machine is nothing but one pulley, two masses, M2, M1. Pulley is frictionless, string is inextensible, and string is massless. Okay, these are all the assumptions, usual assumptions. M2 is greater than N1, therefore A2 is downwards and A1 is upwards. Okay, sorry, the acceleration is same, not different because same string. Okay, so same acceleration. Okay. Okay, so let's make free body diagrams. For M1, we experience M1G downwards, A upwards, okay, A upwards, and tension is also upwards. So M1A is equal to tension minus M1G. Okay, this is one equation. Let us that is one equation. Second free body diagram for M2. Okay, so A is downwards, tension is upwards, M2G is also downwards, right? So M2A is equal to M2G minus T. Okay, now you add these. If you add this, you get M1A plus M2A is equal to M2G minus M1G. Okay, so we get acceleration M2 minus M1, M1 plus M2. This is equation number 3. So you get A is equal to M2 minus M1 upon M1 plus M2 into G, right? Now you take the value of A and you put it in the first equation. You can put it in any one. Okay, so M1 into M2 minus M1 upon M1 plus M2 G is equal to T minus M1G. M1G goes this side. Okay, so we get T is equal to M1G plus M1 into M2 minus M1 G upon M1 plus M2. If you calculate this equation, you will get 2. T is equal to 2 into M1 M2 upon M1 plus M2 into G. So you got the acceleration of the bodies and you got the tension in the string. So whenever you get a question, you can use these two formula to solve the questions directly. Okay, let's do one question just to show you that this formula can be used easily. Okay, simple Atwood machine. This is a question from NEET 2020. Okay, question number 8. All right, this is a pulley, string, 6 kg, 4 kg. Okay, we have to find out the acceleration in terms of g. Okay, what was the formula? m2 minus m1 upon m1 plus m2 into g. Okay, g we have to calculate in terms of g, so let's just keep this g as like that only. Okay, so m2 is basically the greater weight, so this comes out to be 6 minus 4 upon 10g, right? So 2 by 10, so g by 5. This is the answer. Okay, simple. That was simple Atwood machine. Simple Atwood machine. Let's talk about spring force. What is spring force? Okay, so imagine there is this string, okay, and there is a force applied to it. Okay, why I have drawn it horizontally? Because we are going to assume we are not going to assume the influence of gravity on this spring right now. It will be used later on, but not right now. Okay, fine. So this force is being applied. As a result of this force, there will be a change in length called delta x. Okay, now if delta x, it's known as elongation. So if the elongation is not too much as a result of the force, then we can say F is equal to kx, mod of kx. Okay, and k is called spring constant, F is called spring force. Okay, now let's talk about the extension of the string, the elongation of the string. Okay, all right, now this string is an extension of spring. Spring. Okay, now right now the string is hanging, there is no elongation. Okay, but if we drop it and it moves slowly, okay, this is very important, move slowly. This is delta x, let's call it just x. Okay, now s equal to ut plus half at square, right? S is what? X. U is 0, so half gt square. Gt square, right? So x comes out to be mg by k. How? Now half gt square. Okay, f is equal to kx. So f is also equal to mg. mg is equal to kx, because the force on this spring is mg. So mg is equal to kx. So k is equal to mg by x, right? So x is equal to mg by k. Using these equations, you can calculate extension of spring. Now, if this spring is dropped suddenly, okay, the scene changes, because this object will acquire kinetic energy and a loss in potential energy, right? So, following conservation of energy, okay, conservation of energy, what do we get? We get mgx. X is the distance it has dropped, right, equals to half how much energy it has, kx square. Okay, so x becomes 2 mg by k, or k becomes 2 mg by x. Okay, right? Very simple. I know you need a break, but this is a recorded video. You can just pause and take your break, right? I cannot take a break. Okay, so we will do a question for this. Okay, one question 9. Okay, okay, so does this look similar? So this weight is providing, because of this weight there is a tension in this rope T, and as this is a constrained motion, there is another tension T here, therefore you get a tension here 2T, which will equal to the spring force. So F is equal to 2T. Okay, F is equal to 2T. What we have to calculate? We have to calculate the extension, right? So F is equal to 2T. So 2T is equal to kx, right? 2T is equal to kx. T is equal to mg. T is equal to mg. Oh, I'm so tired. T is equal to mg. So we just put this in. So 2mg is equal to kx. X is equal to 2mg by k. All right. Simple. 2T is equal to spring force. 2T is equal to kx, spring constant, right? T is equal to mg, right? T is equal to mg. T is equal to mg. So therefore 2mg is equal to kx, right? So x is equal to 2mg by k. Simple. Okay. We are done with spring force. Let's talk about string versus spring. String versus spring. This is a very small topic. This is a very small topic. Now what you have to understand, as such string, it's inextensible. Okay, inextensible. Sometimes in question string, instead of string you can have rope. So string is inextensible, so tension, it changes instantaneously. Okay, but string is extensible, right? So it cannot change its tension or spring force instantaneously. Very important point. So the equations later can be calculated according to that. Very simple point, right? Okay, this was important to mention, that's why I have included it. Your choice later on. Let's do a string and a string cut question, simple one. Okay, right? So okay, now this is the figure. Okay, now what will happen to the forces on these to the tension on these components once the string is cut? Okay, so first we will calculate at equilibrium, meaning that before the string is cut. So before string is cut, there is this mass, and therefore because of this mass is experiencing weight mg, therefore there is a spring force of F which is equal to mg. Okay, now over here we have weight of 3 mg and we have spring force as well. So we have the tension here. Now tension is equal to 3 mg plus F. So tension is 3 mg plus mg. This equals to 4 mg, right? Okay, but once the string is cut, okay, what are the forces now? There is no tension here, right? There is no tension here. Sorry, we have to find out the acceleration, not the tensions, right? So there is no tension here, so to 3m there is no tension upwards, so therefore the force downwards is 3 mg, right, because of weight, and there is spring force. So how much force is there? 4 mg. Okay, this is the force on the upper weight. What will be the acceleration? The acceleration will be 4 mg. Okay, there is no tension upwards, but you have F and 3 mg, so this comes out to be 4 by 3g. Okay, so net force is 4 mg and you divide by 3 mg because it's in free fall, right? It's in free fall, so 3m. Net acceleration is 4 by 3g. Now talking about the weight below, right? For it the situation has not changed, because we are talking about just after the string is cut. Okay, so this is experiencing the same string force, therefore acceleration on it is 0. Okay, how? It's still experiencing a force of 2 mg upwards, mg upwards and mg downwards. Okay, cool. Okay, we did string cut. Let's do combination of spring. Combination of spring. Combination of spring. So like we talked about spring before. So spring has certain spring force. It has a spring constant, right, which is K. Okay. Now if we add two springs in series, meaning next to each other, so let us say this is one spring with a spring constant K1, and then there is another spring with a spring constant K2. Okay, so the combined spring constant becomes 1 upon K1 plus 1 upon K2, K net. This becomes K1 K2 upon K1 plus K2. But if it's in parallel, okay, K1 K2, then K net becomes equal to K1 plus K2. Okay. Now similarly, if we talk about using these concepts in studying parts of spring, parts of spring. Now if you have this spring, okay, and you cut it into two parts, two equal halves, okay, two equal halves. So earlier it had a spring constant K and a length of L, but if you cut it into two equal parts, okay, the spring constant becomes double and the length becomes half. If it were 3, then K would become 3K and so on. So NK comma L by L if equal parts. So you can say K is inversely proportional to L. K is inversely proportional to L. Sorry, we moved a bit faster, but theoretically we have to cover so many concepts, right? Okay, let's talk about recoil of gun. Once again we have come back to momentum. Okay, so imagine you have this gun and a bullet is fired. Okay, now the mass of the bullet is m and velocity of bullet is vb. Okay, mass of gun is capital M and recoil velocity of the gun is vg. So using conservation of linear momentum, mvg is equal to, not conservation of linear momentum, I'm so sorry, using the third law, and conservation of momentum, both, we get mvg is equal to mvb. That's all, nothing too complicated. So using conservation of linear momentum or third law, right, you get that. So sometimes what will happen is they will say velocity of bullet is, instead of that they will say velocity of muzzle. Okay, so let's do a question. So bullet of mass 10 gram is fired from a gun, a bullet of mass 10 gram. So gun is here, I should not have drawn the gun again. Mass of gun is mass of bullet is 10 gram. Okay, mass of bullet is 10 gram. Mass of gun is 1 kg. No, recoil velocity is 5 meter per second. Okay, 5 meter per second. We have to find velocity of muzzle, so velocity of bullet, right? So mvg is equal to mvb. This equals to 10 into 10 raised to power minus 3 kg, because kg is SI unit, right? So 10 raised to the power minus 2 kg. So we have 5 is equal to 10 raised to the power minus 2 into VB. VB comes out to be 500 meter per second. Simple. That's the answer. Okay, let me have a sip of water and then we do the last topic for today. Rocket propulsion. So I'm not going to draw the whole rocket, I'll just draw a free body diagram. Okay, so think that this is your rocket. Okay, rocket R. Now the rocket propulsion, you can say, is the variable mass system. Okay, variable mass system. So it's going up because of a certain thrust which is applied to the rocket as a result of the burning of the fuel, which causes a force due to the force of exhaust gas. Okay, so force of thrust is equal to force of exhaust gas. Okay, so here force of exhaust gas, now the velocity is constant but the mass is changing, therefore this is equal to V dm by dt. Dm by dt is nothing but rate of burn of fuel. Okay, this is in kg per second, right? How do we get all this? So let us assume at time 0 mass of rocket is m0 and velocity is v0. T is equal to 0. Okay, then at time t is equal to t, mass is m, velocity is v. Okay, and the velocity of exhaust gas, which is constant, is u. Okay, so now value of u is equal to velocity of exhaust gas with respect to ground minus velocity of rocket with respect to ground. Okay, so force of thrust or force of rocket becomes equal to u dm by dt. Okay, dm by dt, and v is equal to v0 plus u log of natural log of e m0 by m0. Sorry, m0 by n, right? Last thing, F thrust up, F exhaust, weight of rocket is down, acceleration is up, right? So ma is equal to F thrust minus mg. So acceleration of rocket is F thrust minus mg by mass of rocket. This was all about rocket propulsion. You don't need to study more. I'm talking this with reference to NEET, not JEE. Let's do one question related to rocket and let's end the class. Okay. Now this question is from AIPMT 1994. Okay. This is a very simple question. Rate of burn of fuel is 1 kg per second, right? Fuel is ejected from rocket at 60 km per second. So U is 60 km per second. We have to find out F. F is what? U into dm by dt. Now U is in kilometers, okay? Kilometer per second. So therefore 60 into 10 raised to power 3 into 1 is equal to 60,000 Newton. That's your answer. And with that, we are done. So we did lots of questions today. We did a lot of topics. I fumbled a bit in between, but that's okay. Physics is not a rote topic. You need to understand the concept. You need to solve the question at hand at that moment, right? So thank you everyone. See you next time. Bye bye.